This video will just be a quick proof by induction of the binomial theorem, as well as a similar proof of a generalization called Abel's binomial theorem. So we'll start with the usual binomial theorem, which states that if I have an expression like this, x plus alpha to the n, this is the sum from k goes to from 0 to n of x to the n minus k times alpha to the k. I'm going to do something a little strange here. So I'm going to actually peel off the k equals 0 term, which you can check as x to the n. And so the remaining terms of the sum will now go from 1 up to n. Everything else will be the same. And so now I'm going to rearrange things a little bit. So I'm going to have the difference here, x plus alpha to the n minus x to the n equaling the sum that I just wrote. Okay, and finally, so you'll notice since k is going from 1 to n and I'm summing terms which have an alpha to the k in them, every one of these terms has a common factor of alpha. So I'm actually going to just divide that out. If I divide both sides by alpha. Now I can take this dividing by alpha into each term individually, and that just translates into reducing this exponent by 1. Alright, so this might seem a little strange, but it will make sense when I talk about the generalization of the theorem by Abel. First I want to quickly prove this one by induction. So I'll leave you to check the base case, which you can take to be n equals 0 or 1, doesn't really matter. In the form that I've written it down here, n would have to at least be 1, so check n equals 1. Okay, so now let's call this star. So let's assume that star holds for some value of n. Okay, so the way I want to prove this now is by doing integration on the variable x. We don't really need to know too much about integration. All you have to know is that if you have a polynomial, or more specifically a power, that the indefinite integral has this form. So it's just the reverse power rule. And we have to remember this integration constant. Anyway, so we can apply that to the left-hand side. That's going to give us this. All over alpha. And in the right, I can just integrate this thing term by term. So my exponent is n minus k, which means I'm going to turn it into n minus k plus 1. And the alpha is just a constant, so that's going to be left unchanged. Finally, I'm going to put in my c. Okay, so now the first thing to notice is this 1 over n plus 1, we can multiply it over to the right. So you can check that when you do that, these two expressions must be equal. If I just multiply the n plus 1 over to the sum, and to be really particular about it, the n plus 1 should also multiply to c, but because c is just an integration constant, which we're yet to determine, I'm just going to still call it c. So this c is not really the same as the first c that I wrote, but it doesn't matter. We're just going to determine it after. Okay, so now what we want is to is to turn all the n's that occur in star into n plus 1s. One of them is already taken care of, actually. So here we can rewrite this a little bit differently as n plus 1 minus k, and that has the correct form. This stuff you can prove using binomial identities, that's actually n plus 1 choose k, which is exactly what you want. And then the final occurrence of n is at the top of this sum. See, in star, we're summing from 1 to n, so to complete the induction, we should have a sum from 1 to n plus 1, and it should consist of terms of this form, which we have written here. I'm just going to erase this stuff and replace it with n plus 1 choose k to make things clearer. Now, we have a c here. So the question is, what would c need to be? What value of c will give us what we want? Well, in order to absorb c into the sum, we need it to be like what the n plus first term of this sum would be, if there was an n plus first term. So c should equal, let's see, so when I put k equals n plus 1, I'm going to get n plus 1 choose n plus 1 times x to the n plus 1 minus n plus 1 alpha to the n plus 1 minus 1. And this all works out just to alpha to the n. So our goal is to try and show that c must equal alpha to the n. When determining integration constants, the usual method is just to pick a particular value for the variable. And in this case, the simplest choice would be x equal to 0. So if we set x equals 0, on the left-hand side, we're going to get 0 plus alpha to the n plus 1 minus 0 to the n plus 1 all over alpha, which is alpha to the n. And you can check that the right-hand side is just going to be equal to c. So all the terms in the sum will actually vanish when I set x equals 0. And so we get exactly the result that we anticipated just by putting n plus 1 into the sum end. So c equals alpha to the n, and so star is proved. Okay. So now, in order to proceeding to Abel's binomial theorem, I want to actually start from this quotient here. And now I'm going to leave this part of the sum the same as it was, only I'm going to change the x and the alpha to these values. So you'll notice this is actually, it very closely resembles the original binomial theorem, star, in that I have a sum from 1 to n of n choose k times something to a minus k and another thing to the k minus 1. However, in the original binomial theorem, the base is independent of k, whereas here we're actually incrementing or decrementing. Is that a word? I don't know. I think it is. Increasing and decreasing x and alpha respectively by multiples of this other value beta, which can actually be anything. And in fact, if beta equals 0, you can quickly see that we just get the usual binomial theorem. Okay. So this is, maybe I'll call this double star. this is the binomial theorem of Abel. And we can actually prove it by induction. It's in a very similar way to how we proved the original binomial theorem. It is a little trickier, as we'll see, but the beginning part is the same. So the base case is n equals 1, which you can check, and it's not so bad. So now we're going to do the same as we did before. Assume the double star holds for some value of n. And just like before, we're going to integrate. So I'm going to kind of skip a little bit of this. So if you integrate both sides and multiply the n plus 1 over, a lot of it is the same at this stage as in the previous proof. We still have a sum from 1 to n. We have an n choose k. From this x plus k beta term, we're going to have a 1 over n minus k plus 1, and then that exponent will be incremented by 1. The alpha term will stay the same, just like before. Plus an integration constant, and I also have multiplied the n plus 1 on the left over to the right, so I'm going to write the n plus 1 over there. Okay, and furthermore, this all reduces to n plus 1 choose k, just like before. Okay. And I'm going to actually also change that exponent on x. X plus k beta. So the similarities stop here, although we can guess a value for c. So what should c be equal to? So just like before, like we have an n plus 1 in the exponent, we have an n plus 1 with the n choose k, or n plus 1 choose k. We only have this top of the summation, which needs to be replaced with n plus 1. Another way to say that is that c needs to be what the n plus first term of the sum would be if it had one. So c should be n plus 1, choose n plus 1, times x plus n plus 1 beta to the n plus 1 minus n plus 1, and then times alpha minus n plus 1 beta to the n plus 1 minus 1. And that all simplifies to just give us this. Alpha minus n plus 1 beta to the n. Now we haven't shown that c is equal to this, but this gives us a bit of a guiding principle to follow. It turns out that putting x equals 0 in our integrated equation doesn't really help that much, because like the reason it was so useful before was because all these terms vanished, but now they have k beta in them, so that just won't happen anymore. The way that you would see what the choice of x should be is that we can make alpha minus n plus 1 beta to the n appear on the left-hand side by choosing a suitable value of x. And that value is given by this. So minus n plus 1 times beta. Let's see what happens when we put that in the left and the right. By the way, let me also just give this equation a name. Maybe I'll call it triple star. I'm not very creative with my names. So double star and triple star. Okay, so in the triple star, let's see what happens. So we have a negative n plus 1 beta plus alpha, all to the n plus 1, minus negative n plus 1 beta, all to the n plus 1, all divided by alpha. This negative sign, I'm going to pull it out. So it's going to be negative 1 to the n plus 1 actually, because the power has to apply to both. This is going to be equal to the sum that we have over here. N plus 1 choose k, sorry. Negative n plus 1 beta plus k beta to the n plus 1 minus k, alpha minus k beta to the k minus 1, and then plus c. All right, now I want to actually also sub in this value of x into double star. So let's just recall double star. This is x plus alpha to the n minus x to the n over alpha, and then the original sum we had. And so it's going to be n plus 1 beta plus alpha to the n minus, I'll let you check that this is what we get there. And then for the rest of it, we're going from k equals 1 to n, and choose k, negative 1 to the, I'm sorry. This to the n minus k times alpha minus k beta, k minus 1. And on this one, there is no plus c. So now, this just looks like an enormous mess. But there is a little bit of hope, because these two terms almost match. See, the only difference is the powers here. So if I multiplied the entirety of the double star by the factor n plus 1 beta, then they'd have matching powers for n plus 1 beta. But then they would also have opposite sign. So the idea is we want to multiply by this factor and then add those two equations together to cancel it off. So the idea is to work out the triple star plus n plus 1 beta times the double star. And when all the dust settles, you actually just get this on the left-hand side. Which I will let you work out if you like. But you'll notice this is exactly what we said the constant c was supposed to be. So it feels like we're on the right track. This is the left-hand side. Now we also need to work out the right-hand sides. This seems like it'll be quite difficult, but what we know actually, or what we would suspect, is that there'll be a lot of cancellation, because, I mean, we're trying to show c is actually equal to this left-hand side as it is. And so whatever these sums are, they should, ideally, they should cancel out. But we have to prove that. So if we can show that n plus 1 beta times this sum on the right-hand side of double star actually equals the negative of the sum in the triple star, then we will be done. Because when you add those, the sums will cancel and you'll just be left with C. Okay. So let's not write down both of the sums. Let's just work out the right-hand side of double star times n plus 1 beta. Okay, so we can see double star at the top there. So this is going to be the sum of an n choose k with a negative n plus 1 beta plus k beta to n minus k minus k beta k minus 1 times n plus 1 times beta. And we want it to try, or we want to try and make it resemble the right-hand side of a triple star. At least the part with the sum. Okay, well the first thing is that sum has an n plus 1 choose k, and we already know to make n plus 1 choose k, we've done this already a couple times. We need n plus 1 over n plus 1 minus k to multiply to n choose k. So we already have an n plus 1. We don't have an n plus 1 minus k, but we can always just introduce it and then make sure that we multiply it back to balance everything out. So we put that in, and this gives us n plus 1 choose k here. And I've introduced this, and now I'm just going to write the rest of it, all of this stuff. Okay, and actually in here, I'm going to factor out the beta, and I'm also going to take out the negative 1. So that is going to result in a negative 1 to the n minus k, n plus 1 minus k times beta. I forgot this beta at the end here. Oops. Sorry about that. Alright, so this is still a bit of a mess. But you'll notice actually, if I take this n plus 1 minus k and this beta, multiply them together, that actually will increase the power of this thing by exactly 1. So I'm going to just get rid of those and change this guy to an n minus k plus 1. So sum of n plus 1 choose k times all of that stuff. Now let's compare with triple star. I'm just going to grab this and put that right below. So let's see what the difference is. So this was triple star had a plus C, so this is triple star. Now I can also factor out the minus sign in this like beta plus k beta term. So what we're going to get with that is just minus 1 Sorry, having technical difficulties. So we have a -1 to the n plus 1 minus k. And then we had an n plus 1 minus k times beta to the n plus 1 minus k. Alpha minus k beta to the k minus 1 plus a c. Okay, so now, if we compare these two sums, you'll notice that they're almost exactly identical, with the exception of these powers here. And so they're actually, they differ by a single factor of -1. And so when you add those two together, they're going to perfectly cancel. So if we go back up here to this right-hand side, this is actually just going to be equal to c. And that proves that c equals the value which we guess that it should. C is equal to alpha minus n plus 1 beta to the n. And so Abel's binomial theorem is proved.